Today, we will be looking at geometric progression. We will be looking at geometric progression. We will be looking at the nth term of a geometric progression. We will also be looking at the sum of terms of a geometric progression, whether they be finite or infinite. So let's look at this set of numbers and let's see the kind of pattern they follow. Now we have the first term, 1, and this is denoted by A1. A1 is the first term. We have the second term, 3. A2 represents the second term. The third term is 9, represented by A3. The fourth term is 27, and the fourth term is denoted as A4. And we have a fifth term, 81, which is denoted as A5. So multiplying the first term by 3 gives us 3. That is 1 times 3 gives us 3. Multiplying the second term 3 by 3 gives us 9. And then multiplying the third term by 3, which is 9 times 3, gives us 27. And then multiplying the fourth term, which is 27, by 3 gives us 81. So one common thing we can see is that we have a common ratio, that is 1 times 3 gives us 3, 3 times 3 gives us 9, 9 times 3 gives us 27, and 27 by 3 gives us 81. So this is a geometric progression, and is a sequence or series where the ratio of any term and its previous term is a constant number and is the same throughout the progression. Now, there is a common number that is being multiplied to each of them, each of the terms. The first term being 1, then you multiply by 3 to get the second term. Second term being 3 multiplied by 3 gives us the third term, which is 9. 9 times 3 gives us 27, gives us the fourth term. 27 times 3 gives us 81, the fifth term. Here we have a sequence. Sequence because we have 1, 3, 9, 27, 9, 81. So we have terms following each other, and we have a definite number. We only have 5 terms in this particular sequence. So we can call it a finite geometric progression sequence. I come again, a finite because we have a definite number of terms, in this case 5. A geometric progression because we have multiples of 3, which is the common ratio throughout this geometric progression. So it's a finite geometric progression sequence. So we look at the geometric progression: 1, 3, 9, 27, and 81. They all have a common ratio of 3, and the first term being 1 and the last term being 81. And that last term is the fifth term. So you have A1 representing the first term, A2 representing the second term, A3 representing the third term, A4 representing the fourth term, and A5 representing the fifth term. So this is an example of a geometric progression. In specific terms, a finite geometric progression which is in sequence. It follows a definite pattern, and each of the numbers or each of the terms are obtained by multiplying 3 to the previous term. Here we'll be looking at the relationships or relationship between one term and the other. And that relationship is a ratio. And if that ratio exists throughout, then we call it a common ratio. Now, we have the first term, A1, which is 1, the second term, A2, which is 3. Let's see whether there's a relationship between A1 and A2. A1 and A2. So let's say A2 divided by A1. A2 being 3 and divided by A1 being 1. So we have 3 divided by 1, which gives us 3. We'll look at the next set of terms. We'll say A3, which is 9, divided by A2, which is 3. What we're saying invariably is third term divided by second term. And that is 9 over 3, and we have 3. So what we're trying to do is to establish a common ratio across board, not just across one or two terms, but across board. The only way for us to conclude that this is a geometric progression sequence is when all the terms have a common ratio of 3. So we have done A3 divided by A2. We'll move to the next. We'll now say fourth term divided by third term, which is 27 divided by 9, and that gives us 3. Then we'll look at the fifth term divided by the fourth term, that is 81 divided by 27, and that gives us 3. So we notice that there is a ratio 3 which is common to all, and that's why we call it a common ratio. And that common ratio is called or denoted R. So R is the common ratio, and in this particular case, R is 3. Take note that sometimes the ratios can be positive, sometimes the ratios can be negative in some examples, and also take note that sometimes the ratios can be whole numbers, as in this case, and it can also be fractions. Here we will be establishing a particular pattern for the geometric progression, which will eventually lead us to getting a mathematical expression for the nth term, n being any of the terms, the nth term. So in this particular term, A1, n is equals to 1 because n is 1, that is the first term. In this particular one, n is 2, that is, this is term 2, so n here is 2. Here n is 3, that is the third term, and third term is 9. Here n is 4, here n is 5, being 81. So first term A1 is 1, second term A2 is 3, third term A3 is 9, and fourth term A4 is 27, and then fifth term A5 is 81. So we'll be establishing a mathematical equation or designation for each of these terms. So we have already established that there's a common ratio of 3 between the terms, and that our A1 being the first term is 1, and that A2 is established, that is the second term, is established by multiplying 1 by 3. Indirectly, we are saying we are multiplying 1, which is the first term, and is denoted as A1, and by 3, which is this 3 here, which is the common ratio. So A1 times R gives us what? A1R. So this is the mathematical expression for the second term. A2, which is established by multiplying 1, the first term, by the common ratio R. So it is A1 times R, which is A1R. We look at the A3. So in getting to A3, it would be 1 times 3, and then times another 3. And 1 times 3 is 3. 3 times the other 3 is 9. So it can also be expressed as A1, which is this one, times R times R. So A1 times R in two places, which is A1R squared. Before we proceed, I can observe a little pattern. Now, if you add this 1 here, which is the first term, A1, and then you add the 2 here, which is the power of the ratio, 2 plus 1 gives us 3. Let's look at the previous one. What's the power of R here? 1 plus the subscript 1. 1 plus 1 gives us 2. So for each of the terms, the summation of the subscript and the power should give you the term. And we'll see whether that is correct for A4, which is fourth term, and also the fifth term. Now, how do we get the fourth term? First term times 3 times another 3 and times another 3. So it is the first term, which is A1, and that 3 multiplied in 3 places means R multiplied in 3 places, which is the common ratio multiplied in 3 places, and that gives us A1 times R raised to the power 3. 3 plus 1, we're just using it as our own personal check, is 4. Now let's look at the fifth term, which is 1 times 3 times 3 times 3 times 3. So 3 is multiplied in 4 places, that is the common ratio is multiplied in 4 places and initially multiplied by the first term. So the first term times the common ratio in 4 places, which is A1R raised to the power 4. 4 plus 1 is 5. We're just adding that in order for us to do our own personal check. Now, what we have seen a pattern that says AN, that is the nth term, is A1 into R into the raised to the power n minus 1. A subscript n is equal to A subscript 1 R raised to the power n minus 1, such that, like we did our personal observation, when you add the power here to what you have as a subscript, it gives you the corresponding subscript here. So n minus 1 plus 1 will give you n. So what we are saying is that all these A2, A3, A4, A5, that is the term n, is simply obtained as we have seen here respectively, and is simply A subscript n, that is any of the terms, is equals to A subscript 1 r raised to power n minus 1. Here we've been successfully able to establish the nth term of a geometric progression. Let's look at A2. A2 will be what? A1 times r. A3, A subscript 3, which is the third term, will be the first term, r raised to power 2. The fourth term, without looking at the one on the right, will be what? A subscript 1, r raised to power 3. Fifth term, A5 or A subscript 5 will be what? A1, that is the first term, multiplied by r raised to power 4. So our general equation, which is what we need to put to heart, which should come handy, is A subscript n, that is the nth term, is equals to the first term and then r into n minus 1. So here we will be doing a quick summary of the nth term of the geometric progression. So we have established that A subscript n, which is the nth term, is equals to the first term multiplied by the common ratio all raised to power n minus 1 bracket close. So it's only the common ratio you are raising to this power, and you're raising it to 1 less than the n term. So if n is 5, for instance, it will give us is equals to A subscript 1, which is the first term, multiplied by r raised to power 5 minus 1. And 5 minus 1 is 4. So you're saying A1 multiplied by r raised to power 4 in the situation where n is equals to 5. Now, what is our an? That is our nth term. What is our a1? A1 is the first term. What is our r? Before r, let's look at what n is. N is the number of terms. So in various cases, you can have different terms. So for instance, if we want to know the first term, our n will be 1. And then anywhere we see n, we substitute with 1. If we're trying to find out the third or fourth term in a geometric progression, if it is the fourth term, then n will be 4. And then wherever we see 4, or wherever we see n, we put 4. So depending on the number of term or the nth term we're looking at, r is the common ratio. And take note that the common ratio can be positive or negative, and it could also be a fraction. Let's also take note of the sum of n terms. That is the sum of the number of terms from a geometric progression. The sum of n terms is equals to the first term times, open this bracket, 1 minus the common ratio raised to power n, that is the number of terms we're considering, bracket close, all over 1 minus r. It will be good to take note here that the sum of n terms here is for a finite sequence, or series. That is, we know exactly the number of terms in that sequence or series, and that's why we have the subscript n, where n is the terms in that sequence or series. So sum of n terms, which is S subscript n, is the sum of n terms of a finite geometric progression. So this is for a finite geometric progression where A1 is what? The first term. N is the number of terms we are considering to find the sum. So you may have a geometric progression. You want to find the first two terms or first three terms. So if it's the first three terms, n will be equals to 3. That is the n we're using here will be equals to 3, and it will be S subscript 3. And then R is the common ratio, which, like I said, could be positive, could be negative, and it could be a whole number or even a fraction. So please take note of this particular sum of n terms, which will be used for a geometric progression. So note, for an infinite geometric progression, the sum of the terms, that is the sum to infinity, is equals to A1 all over 1 minus R. A1, where S infinity is, or S infinite, is the sum of infinite terms for this geometric progression. And we know what our A1 is. Our A1 is the first term. R is the common ratio. But please take note that for you to have the sum in an infinite sequence or series, your common ratio, the absolute value of your common ratio, must be less than 1. In essence, it must be a fraction. It must be less than 1. Anything less than 1 is a fraction. So that is the only way in which the summation will have a convergence. If not, if your R or the ratio is greater than 1, there will be no convergence, and therefore the sum to infinity will also tend to infinity, whether it's positive or negative. So let's look at a quick example of how to find the sum of n terms of this geometric progression. Now, if you look at A1 means term 1, A2 term 2, A3 term 3, A4 term 4, and A5 term 5. Now you see this first set of numbers, there are 5 of them, so it is finite because it is established that there are only 5. The first having comma, that is, there is another number after it, 3, 9, 27, and 81. These are sequenced numbers, and therefore they have a particular number of terms, and they also have a common ratio. So the first set of numbers on top with the commas are finite geometric progression sequence. Now let's look at the numbers below. You have 1 plus 3 plus 9 plus 27 plus 81. 5 terms, which we know for a fact. They have a common ratio, and it is a geometric progression. So in this particular case, it is a series and not a sequence. So it is a finite geometric progression series. So like we mentioned, the first set of terms above, they are finite geometric progression sequence, and then the second terms set of numbers below, because of the addition sign, it could be subtraction, but in this case addition, they are a finite geometric progression series. The commas make these ones on top a sequence, and then the arithmetic operation here makes it a series. Like I said, it could be a negative sign, but here it's a positive sign. Now let's see whether we can add these geometric progression. So we have 1 plus 3 plus 9 plus 27 and plus 81. If we use our calculator, we have 121. But these are 5 terms. It's easy to add them. What about if there were 100 or 200 terms? How would we add them in a more simplified manner? And that's the reason why we were able to come up with the sum of n terms. And that sum of n terms for a finite geometric progression, either as a sequence or series, is equals to sum of n terms is equals to a1, which is the first term, into the bracket 1 minus r being the common ratio raised to power n being the nth term, all divided by 1 minus r. So if our n is 5, that is, we want to find the sum of the 5 terms, we simply substitute our a1 is the first term, which is 1. Our common ratio is 3, n being 5, and then we substitute accordingly. And then we have this expression, and by the time we simplify, we have 1 minus 243 all over 1 minus 3, which is equals to minus 242 divided by minus 2. So let's just look at how we substituted. What is our a1? 1, because our first term is 1. Bracket open, 1 minus r raised to power n. What is our r? Common ratio is 3. What is the n? We're looking for the sum of the 5 terms, so n is 5. So we're saying 3 raised to power 5. That is the common ratio 3 raised to power the number of terms n, which is 5, all divided by 1 minus r, and we already established our r to be 3. So if we simplify, if you multiply 1 by everything here, it remains the same. So we have 1 minus 3 raised to power 5 is 243. We can use our calculator to check. Divided by 1 minus 3. So 1 minus 243 will give you negative 242. Divided by 1 minus 3 is minus 2. So if you divide this, the negative here cancels the negative here. 2 into 2, you have 1. 2 into 4, you have 2. 2 into 2, you have 1. So you have 121, which corresponds with what we calculated above. So your sum of n terms given by this particular formula is very useful in geometric progressions. We will quickly look at this set of numbers: 16, 8, 4, 2, 1, and 0.5. 16, 8, 4, 2, 1, and 0.5. You see that after the 0.5, the dot continues infinitely. So there is no established end to this particular set of numbers, and therefore That's why this is an infinite qualification for this set of numbers. Now, what is the relationship? Now, the second term divided by the first term, that's 8 divided by 16, is half. 4 divided by 8 is 1 over 2, which is also half. 2 divided by 4, which is also half, that is 1 over 2. And then 1 divided by 2 is half. 0.5 divided by 1 is 0.5, and 0.5 is half. Now we have the dots going on, which is why we said it is infinite. Now we established a common ratio of half, and that makes it a geometric progression. Now we want to find the sum of these infinite terms, and that's given by the equation S is equals to A1 over 1 minus R. A1 being the first term here, which is 16, and then R being the common ratio, which we have established as half. So let's substitute accordingly. So we have A1 over 1 minus R, A1 being 16, 1 minus R, R being half, so it will be 1 minus half, and that gives us 16 over half. So if we simplify that further, we have 16 over half. Now what do we do in order to simplify this? So if we multiply the top by 2 and also the base by 2, we're able to clear the fraction in the denominator, and that's the whole objective why we actually multiplied by 2. So half times 2 is 1, so that cancels out, and then 16 times 2 is 32. So what this tells you and I is that this infinite geometric progression sequence will tend to 32 as we keep adding. So it will become either something very, very close to 32 or exactly 32, but not more. Now we can even see that from this trend. 16 plus 8 is 24. 24 plus 4 is 28. 28 plus 2, 30. 30 plus 1, 31. 31 plus 0.5, that is 31.5. If we keep adding the terms continuously, we will tend towards 32. So that's why the sum to infinity is equals to 32. And remember that there is a condition where R, the absolute value of R, has to be less than 1. Remember the absolute value of R, our R is half, and definitely half is less than 1. And that's why we can use this to establish the sum to infinity of this particular sequence as 32. So let's quickly answer these questions as we begin to round up. So the question here is, what kind of progression does the above pattern of numbers follow? What kind of progression does the above pattern of numbers follow? So let's look at the relationship. 1 becomes 2, 2 becomes 4, 4 becomes 8. So there is a common ratio of 2. You multiply 2 in each of them. If we take the second number, divide the first, 2 divided by 1 is 2. Third divided by the second number, 4 divided by 2 is 2, and so on and so forth. So we're able to establish a common ratio, which is 2. There is 1, 2, 3, 4, 5. There are a definite number of terms, so it's finite. It's a geometric progression. So we can say that it is a geometric progression. So that's the progression it follows. But if we want to be more specific, and then we can see that there are commas, so it's also a finite geometric progression sequence. So it's a finite geometric progression sequence. So let's quickly find the sum of n terms of this particular geometric progression. So we have sum of n terms is equals to a1, 1 minus r raised by n, all over 1 minus r. Our a1 is 1, our r is 2. So what we just want to do is we want to express the sum of n terms in terms of n. So we'll just substitute accordingly. So we have a1 being 1, r being 2. How did we get our ratio as 2? We can see that 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So we have a common ratio of r, which is 2. And then we say 2 raised by n because we have r raised by n, all over 1 minus 2, that is 1 minus r. And if we simplify this further, we have is equals to, so 1 multiplied by all this, it remains this, so 1 minus 2 raised by n divided by 1 minus 2, which is minus 1. So we have positive on top divided by negative. The negative can go on top. So what we are saying is 1 minus 2n, and then we put a negative sign outside. By the time we open up these brackets, so minus 1 times 1 is minus 1, minus 1 times minus 2 raised by n, it now becomes positive. So what we have is 2 raised by n minus 1. So this negative sign here, minus 1 times 1, we have minus 1 here, and then minus 1 times minus 2 raised by n. Minus times minus is plus, so 2 raised by n is now positive. So we have succeeded in finding the nth term, or rather the sum of n terms. We have succeeded in finding the sum of n terms for this particular expression. And I can prove that now. So let's assume we want to find the sum of these first two terms. So then we are saying that n is 2. So we just need to come here. So 2 raised to power 2, because n is 2. So 2 raised to power n, and 2 raised to power 2 is 4. 4 minus 1 is 3. So let's check whether the sum of the first two terms is 3. The first two terms, first one is 1, the second term is 2. So 1 plus 2 is 3. And that satisfies this expression, and that is the sum of n terms. Thank you.